So now let us understand what does independence of random variables means. So let us take two random variables x and y. Then they are called to be independent of each other if for any set B1 and B2 which are Borel on real line, the probability that x belongs to B1 and y belongs to B2 is given by probability that x belongs to B1 multiplied by probability y belongs to B2. And here, when I say probability x belongs to B1, it means probability of all omega such that x omega is in B1. Similarly, x and their joint distribution is also defined. So this should be true for every possible B1 and B2 set. So let us take a specific type of Borel sets, which we also used when we defined the CDF and the definition of random variable, uh, which is of the form minus infinity comma x. So let us take b1 equal to minus infinity comma x and b2 equal to minus infinity comma y. Then the probability that x belongs to b1 and y belongs to b2 is nothing but probability that x is less than or equal to small x and y is less than or equal to small y, which will be nothing but the CDF at x comma y of the joint CDF of x comma y. Similarly, the two terms would be equal to CDF of x and CDF of y. So this means equivalent condition would be that the joint CDF at x comma y is equal to the CDF of x into CDF of y, respectively at x and y. Or in other words, you can say probability that x is less than or equal to x, comma y is less than or equal to small y is equal to p probability of x less than or equal to small x and probability of y less than or equal to y. So now I state a result that if you can show this for every possible x and y, then also x and y are independent. And we know that if x and y are independent, then this condition is true. So x and y are independent to each other if and only if the CDF at joint CDF is equal to the product of individual CDFs at each x and y. So this is a sufficient and necessary condition which you can prove for two random variables to be equal to independent. And then you can prove that if this condition is true, then for any set Borel's of Borel set, you can show the given condition that probability for of x belongs to b1 and y belongs to b2 is equal to individual product of individual probabilities. So this is the main rule which you can check always, or you can also check the CDF, or you can have to check for every every Borel set B1 and B2. This is true. For discrete random variable, if you can take also a singleton elements. So let's take B1 consisting on only one element x and B2 equal to only value y. Then this is equivalent to saying that probability that x takes value x and y takes value y is equal to probability that x is x and y is equal to y. And if you can show this for every possible x and y, then you can prove that for any Borel set containing some range of values, also this condition will be true. So this is also a sufficient condition for the random variables that if you can show that for every possible values of x, the PMF, these are joint PMF and these are individual PMF, is a joint PDF of x comma y, PMF of x comma y is equal to the product of individual PMFs at x and y, then also the x and y would be independent. This is a result for discrete random variable. Similarly, for continuous random variable, if you take Borel sets of this form, x comma x plus epsilon, then the probability that x belongs to b1 is nothing but the PDF multiplied by the length of the interval, which is epsilon. So this is the PDF at x, PDF of x at small x into epsilon, and this is PDF of y into epsilon. And this is the joint PDF at x comma y multiplied by epsilon square. So this condition would be equivalent to the joint PDF multiplied by epsilon square should be equal to the PDF of x multiplied by epsilon into PDF of y multiplied by epsilon, which is equivalently written by this condition. So for this continuous random variable, this is a necessary condition, insufficient condition. If you can prove that the PDF, joint PDF is the multiplication of individual PDF, then these are independent. So you can try to prove that if this condition is true, then for every Borel set, this condition will also be true. That simply involves just the integration over the appropriate intervals. Now let us come back to the conditional distribution. So we have seen conditional distribution for normally events. But what is the conditional probability A given B? Here we define the conditional distribution of random variables. So let us assume an event is given to you, A, and then condition on this event, we want to compute the distribution of random variable X. So this is formally defined as, in the same way as we define the conditioning on events. So recall conditioning B given A, condition on A, probability of B is denoted by probability B given A is equal to probability of B intersection A divided by probability of A. So similarly here also, the B, I will say the probability law of X condition on A of B is equal to probability that if there was no conditioning, then this will be equal to probability of pre-image of B or probability of all omega such that X omega is in B. So this is a event. So now if we condition on A, we will say that probability of this B given A is nothing but probability of this pre-image condition on A. Or in other words, we can also say this is probability by using the definition of condition of probability of some set given A is equal to probability of C intersection A divided by probability of A. And C here is nothing but probability of omega such that X omega belongs to B. So if you write this down, this is nothing but this A is a some event. So it is set of some omega which belongs to A. So we can rewrite this numerator as probability of all omega such that X omega is in B and omega is in A divided by probability of A or probability of set omega such that omega belongs to A. So this is the formal definition of conditional distribution of a random variable X given an event A. So from the general definition, we can also define the conditional CDF. Remember, for conditional CDF, we only have to put, instead of B, we have to put minus infinity to X. So if we put that, we get the CDF, the probability that this X is less than or equal to small x given A. So this is equal to probability law of the set omega x below omega less than or equal to x given A. So using the same definition and condition probability, this is nothing but the probability that of all omega such that X omega is less than equal to X and omega belongs to A. So this is the intersection of A and the given set pre-image of minus infinity comma X. So recall one is in terms of event and second term is given as a pre-image of a set of real line. Okay, and real line is nothing but the range of this random variable or the codomain of this random variable. So one is written given in terms of codomain. So you have to take the pre-image. So that's why I say omega such that X omega less than or equal to X. This is nothing but the pre-image of minus infinity comma X. And this is in form of the subset of the omega, capital omega itself. So let's see one example. Let us take a case where the person is arriving between 2 to 3 p.m. and his arrival is a random outcome. So the sample space will be from 0 to 1, where 0 denotes 2 p.m. and 1 denotes 3 p.m. Then let's define x as a random variable equal to x omega equal to omega. So omega denotes the arrival of the person in hours. So let event A is 0 to 0.5. This is an event this is defined in the codomain of x omega, but the pre-image of this will be an event, and this just means that x omega is between 0 to 0.5. Okay, or you can define as a event which is in the sample space, subset of a sample space from 0 to 0.5, which means the omega is made from all omega, which is between 0 and 0.5. So what is the probability of A? Probability of A would be just 0.5 if you take the uniform measure. Okay, let's assume uniform measure here. You can take any other measure also, correspondingly define the probability of A. Now condition on this event. So if you see this event, this event occurs when the person arrives in the first half hour. So condition that the first person arrives in 1 hour, what is the distribution of X? So for that, we would require, for this CDF, we would require this joint, probability of the intersection and probability of A. Probability of A, we already know, which is half. So let's compute this intersection. So again, recall this intersection is nothing but probability of the pre-image of, so this intersection is the intersection of pre-image of minus infinity comma x and A. And then we have to take the probability of this, and we assume the uniform measure here. So this pre-image can also be written as probability that omega such that x omega is less than or equal to x. And then the other condition is when you take intersection, the omega also need to be in A. So omega belongs to A means omega should be between 0 and 0.5. And the first condition says omega should be less than or equal to x. So now this is the complete intersection of the two events. And then I have to take the probability to compute the numerator. So this depends on x. So if x is less than or equal to 0, there will not be, this condition will be that omega should be less than 0. And then this condition is omega is greater than 0. So there is no intersection and this will be a null set. So probability of null set would be 0. So the CDF would be this probability multiplied by probability of A, which will be 0. Similarly, if x is 0, there is only one value which will satisfy both conditions, that is the sentence at 0. Probability of this is also 0, so CDF is also 0. When x is between 0 and 0.5, then the intersection, this set will be smaller. So the intersection would be 0 to x. The probability of this will be just x minus 0x. And the CDF would be x divided by half, which is 2x. And when x is greater than 0.5, this set contains this set. So intersection would be this set only, which is 0 to 0.5. And the probability of this is 0.5. And if you divide by this, you get 1. So this CDF would be 0 until x equals 0. Then it rises as 2x until it reaches 0.5, and then it becomes 1. From CDF, you can again, right, so that is conditional CDF. Now, recall that what we have defined is conditional distribution of a random variable given an event A, where A was defined as a subset of sample space, and the numerator was in terms of the pre-image of set B. Now, this set can also be defined as a in terms of random variable. So here you see, if you compare it with probability of C given A, right, then there C and A both are subsets of sample space and both are events. What is new here is when we say that we want to define conditional distribution of random variable, the numerator was instead given in terms of the random variable. Instead of saying specify a event C, we specified B and then said this is equivalent to the event omega. This is equivalent to the event which consists of all omega such that x omega belongs to B. So once we say for numerator, we can also write the conditioning event in terms of x also. So these both are equivalent. Either we'd say in terms of random variable or say in terms of sample space, they are equivalent kind of notations. So if we say that probability, if we denote instead of A, we condition on this set, which is nothing but the pre-image of C, which is made from all omega such that x omega lies in C. So then we can just use the notation that this is a probability law of x b given c instead of saying x given something, because here both b and c are in terms of x. So this means, this notation means it is the probability that x belongs to b given x belongs to c. And in the normal notation, this means this is the event that pre-image of B, and this is the event pre-image of C. I'm just computing the probability, the pre-image of B, conditional pre-image of C. And this you can define the same way. The probability of this pre-image of B, conditional probability of pre-image of C is nothing but probability of pre-image of B intersection pre-image of C divided by probability of pre-image of C. And the pre-image of B intersection with pre-image of C is nothing but the pre-image of B intersection C. This you can understand. This is made from all omega such that x omega lies in B. This is made from all omega such that x omega lies in C. So intersection will be made from all omega such that the intersection is also in B and C, which is nothing but the pre-image of B intersection C. So this thing is the pre-image of B intersection C divided by the probability of pre-image of C, and which can be written in terms of probability law as probability law of B intersection C divided by probability law of on C. This will be your conditional distribution of B given C. So now extending the definition to include another random variables. So when we talk about this conditioning of probability of C given A, where C and A are events, I said that you can either write them in terms of actual events, which are subsets of sample space, or you can also write them as in terms of random variable x. So you can say a set B, x belongs to set B, which means actually an event which is a pre-image of this set B. And both are equivalent notation, so you can replace either the numerator or the denominator or both with the equivalent representation containing x. And again, because there can be multiple random variables, so you are also free to use other random variables to either replace one or all in terms of those random variables. So let's take x as a random variable and let's take y as another random variable on the same probability space. Then we can also condition on the events of the form of the pre-image of C, which is nothing but omega such that y omega belongs to C. In that case, I'll use this notation, probability that x given y of set B given C, which means probability that x belongs to B, condition that y belongs to C. So in that case, this is equivalent to probability of the pre-image of B with respect to random variable x. This pre-image is with respect to random variable x, and so condition on the pre-image of C with respect to y. So this is the pre-image of C with respect to y. Remember, the pre-image changes with respect to random variable. So if I say the pre-image of B with respect to x, I means all omega such that x omega belongs to B. If I say the pre-image of B with respect to y, I means probability of all omega such that y omega belongs to B. Okay, and both can be very different sets. So this here means in the subscript I say x given y. So they have corresponding relation that X denotes to B and Y maps to C. So this means probability of pre-image of B with respect to X given probability of C with respect to, sorry, probability of pre-image of B with respect to X given pre-image of C with respect to Y. So this is probability that the intersection of pre-image of B with respect to X and probability pre-image of C with respect to Y condition on the probability of pre-image of C with respect to Y. So this denominator you always have the conditioning events probability. So the top, if you see, this is made from all omega such that X omega belongs to B and Y omega belongs to C. So this is a joint probability law on B cross C. Okay. So remember, if you take two random variable X comma Y, the joint B comma C pre-image with respect to X comma Y would be set of all omega such that X omega belongs to B and Y omega belongs to C. So this conditioning probability law is equal to joint probability law on B cross C divided by the probability law on C with respect to Y. Okay, or in simple terms, you can say this is equal to probability of all omega, or those omega such that X omega belongs to B and Y omega belongs to C, divided by probability of all those omega such that Y omega belongs to C. Similarly, you can also define conditional CDFs. So you can say probability conditioning CDF X given Y is equal to probability that X is less than or equal to small x given Y is less than or equal to Y. And you can have any kind of conditioning event in the denominator. If conditional CDF, generally CDF refers to the numerator part, that you are talking about the probability of the form that X is less than or equal to some X. So let us take a few examples. I'll talk specifically for discrete random variables and the continuous random variable. So let's first take discrete random variable. Both X and Y are discrete random variables. Then the probability mass function of X and Y are defined. Let's assume they are Px and Py. So Px, X defines the probability that random variable X takes value X, which is actually saying the probability of the pre-image of singleton set X. Similarly, Py is defined, and let the joint PMF is given by Pxy x comma y, which tells the probability that X takes value small x and Y takes value small y. Or in other words, this is equal to probability of all omega such that X omega is X and Y omega is small y. So the conditional probability is given as now for any two Borel set B1 and B2, probability that X belongs to B1 given Y belongs to B2 is equal to probability that X belongs to B1 and Y belongs to B2 divided by probability that Y belongs to B2. And what is the probability that X belongs to B1 and Y belongs to B2? It is given by adding all the PMF at PMF values as those points which comes in this set. So if I sum over all points xy which comes to B1 cross B2, if I add all these masses, then I'll get the total probability that X takes value in B1 and Y takes value in B2. Similarly, for probability Y belongs to B2, there is no restriction on X, so you can just add all the PMF of Y over all values such that Y belongs to B2. Okay, and then instead of this, you can also see this in the following way. Probability that Y belongs to B2 is that probability that X can take any value but Y belongs to B2. So you can also add the joint PMF of X comma Y or all the pairs such that Y takes value in B2 and X takes any value on the real line. Both will be exactly same. So if I take a special case where both B1 and B2 are singleton set. So normally B1 and B2 can be any Borel sets. They can be combination of different values x can take. But let's take for this case a simple example where b1 and b2 both are singleton sets. So let's take b1 is made from a fixed variable x and b2 is made from another random variable y. So in that case, probability of this x given y, so instead of b, I now have just this singleton set. So probability that x belongs to b1 is nothing but probability that x is equal to x, and probability and the event that y belongs to b2 is just saying that y take is equal to this one. So this, if we put back in this expression, b1 and b2 are singleton elements, so this summation is just on a single element x comma y, and similarly this is also in a single element y. So this will become the probability xy of joint PMF at x comma y divided by the PMF of y at small y. So if I fix y, suppose that the y takes this value, a specific value, the small y, and I talk about a distribution of x. So for a given y, let's denote this as a function of x. Let's denote this by p dash x. Okay, so when I say p dash s, I means probability PMF of x given y. Okay, which is defined as the px joint PMF at x comma y divided by probability of PMF at y. So I want to claim that for if I fix y, then this which is a function of x is actually a valid PMF on this random variable x. Okay, so this means when I say it's a valid PMF, it means if you take any set b, then the probability that x belongs to b given y takes this specific value. So this value is fixed. So condition on this event, the probability x belongs to b is nothing but you add the PMF on all the points, all the values which are in b. Okay, so recall in normal PMF also, when I say probability that x belongs to b without any condition, then that should be, we should be able to write this in terms of summation of all those values of x. So summation of PMF at all those values of x which lie in this set b. Okay, and because it's a discrete random variable, we don't have to talk about all values. We only take the range of x and see what out of this complete range of capital X, how many points are falling in this set B, and we just add the mass at all those points to get this probability. Similarly, if this is a conditional PMF, valid PMF, this means that the probability that X belongs to B condition on this is equal to summation of PMF over all the values which are occurring in B. Okay, this is our claim. So to prove that this claim is true, it's a valid PMF, we have to show that this takes value always between 0 and 1. Also, if I add all those values, it should be equal to 1. Okay, so these two things I need to show to make this is a valid PMF. That should be between 0 to 1, and if you add all the values over the range of x, you should get 1. Then it's a valid PMF. So how do we prove this? To prove this, we have to basically show, recall what is the definition of this. This p dash x is nothing but the conditional PMF, which is given by this. I have to show that this is between 0 and 1. Okay, so this means I have to show that the numerator is greater than 0 and less than the denominator, less than or equal to denominator. So how can I show this? So let's take even as a event of pre-image of x comma y. So this is a set of all omega such that x omega is small x and y omega is small y. And then let's take E2 of all omega such that y omega takes value 1. Okay, then you can see that the probability of E1 is nothing but the PMF of x comma y by definition. So by definition, the PMF, joint PMF at x comma y is the probability of the pre-image of this set. So similarly, probability of E2 is nothing but the PMF of y at small y. Now you can see this E1 is a subset of E2. So E2 is made from all omega such that y omega takes y, and then E1 is made from all omega which satisfy this condition, but there is one more condition. So there will be some omega which in E2 which do not satisfy this. Right? So E1 is a smaller set than E2, is in fact a subset of E2. So probability of E1 should be less than or equal to probability of E2. That was from the probability properties of the probability measure. So this means probability of E1 is less than or equal to probability of E2. This means this is less than or equal to this one. So if you divide them, you will find out that this divided by this is less than or equal to 1. Okay, greater than 0 is easier to prove because this is the probability should be more than 0 always. More than or equal to 0. Okay, next is to prove that the summation is equal to 1. So I'll just put back the value. So this is by definition is the conditional probability which is given by joint PMF divided by the PMF of y. Okay, and then this is a summation over all values of x which belongs to a range of x. So this does not depend on y. So what I can do, I can take this summation in the numerator and just have the denominator common. So when you do that, this is just a summation of a joint on PMF. Okay, now look at this. This is the probability that x omega is small x and y omega is y. And if you add them, this will be equal to probability that x takes any value and y takes this small y. Okay, so this is nothing but just the probability PMF of y at y. Okay, so give some time to understand this. The PMF is the joint PMF values. The x takes value x and the y random variable takes this value small y. And if you add over all the range of x, then you're adding all those values, then doesn't matter what x value takes, you're basically calculating the probability that random variable y takes the value small y. Okay, so these two are equal, so this summation would be just equal to 1. So this is what we get, that the conditional PMF of x given y at small x given small y is nothing but the ratio of the PMF, a joint PMF of xy divided by probability of PMF at y. Now note that the conditional PMF is not defined when there is no mass at y. So if you take any values y says that py is 0, and then you ask what is the conditional probability, then you know if the py is 0, then pxy is less than py and it's also more than 0. So something which is more than or equal to 0 and less than or equal to 0 is just 0. So the joint PMF is also 0 and the denominator is also 0. So this conditional probability would be 0 divided by 0, which is not defined. So it's not possible to define here the conditional PMF if the conditioning event has a 0 probability. Okay. So you have to make sure that when you say condition that y takes value y, you have to make sure that that value is is a non is takes value at least with some probability. So that event occurs with some probability. Okay. And also remember, in this PMF, when y changes its value, the conditional PMF will change. Okay. So this is a function of both x and y. If you change y, also this condition may change. Okay. And of course, it's a PMF with respect to x. So this term is a PMF, valid PMF with respect to random variable x. It means if you fix the value y, and then this can show you the probability of the event that x takes value x. Okay, so I'm fixing the value y, and I'm only looking at events such that y takes small y value, and then I ask, if you change x, the small x, then what is the probability that the random variable takes these small x values? Okay, and those are masses you have. So this function completely, if you fix y and change with respect to x, what you see is a PMF, valid PMF. Okay, now the thing is, so once you change y, the x, the PMF will be very different, right? And it may also happen not just it changes, its range can also change. It may happen that when y is 1, x takes value 1 and 2, and when y is 2, x may take more values like 1, 2, 3. So not just the values, but the range of x may also change when the conditioning event changes. Okay, let's take an example. So we found that there is some probability space and random variable x and y such that only 3 values are possible. Either x and y both are 1, that happens with 1 by 3 probability, or x is 2 and y is 1, or x is 1 and y is 2. That also happens with 1 by 3 probability. Okay, so in that case, you can see if I want to talk about, I want to condition on y. So let's compute the PMF with respect to y first, because it will come in denominator. So probability that y takes value 1, PYY is what? Probability that y takes value 1. So when does y takes value 1? When either x takes 1 or x takes 2. So probability that y takes value 1 is these two events, right? These two outcomes. So the total probability of y would be 2 by 3. Similarly, probability that y takes value 2 is just 1 by 3. Okay, so these are PMFs. And remember, to calculate any probability of any Borel set, you have to just add all the PMFs, right, of all those points which come into the Borel set you are interested in. Now, if I condition that y is equal to 1, right? So if you condition that y equal to 1, x can only take two values, either 1 or 2. Okay, so probability, so if you want to compute the PMF, probability PMF of x given y at x given y. This means probability of x takes value small x given y takes value 1. Okay, so condition that y takes value 1, probability that x takes value small x is nothing but the joint PMF divided by the PDF of y, PMF of y. Okay. By the way, this we also call the marginal PMF. If this is called joint, this is called the marginal PMF of y, or just the PMF of y. So because it takes value 1 and 2, let's compute the value of this for two values. Probability xy when small x is 1 is nothing but the probability that x and y both takes value 1 divided by probability that y takes value 1. Okay, so that is 1 by 3 divided by 2 by 3, 1 by 2. This means out of these two, both are equally likely. So condition that y takes value 1, x takes value 1 with half chance. Similarly, x takes value 2 with also the half chance. Okay, so condition on y takes value 1, there are two values x can take and both are equally likely. Now if I condition on y equal to 2, x only takes one value 1. Okay, and the probability that the joint probability is the joint PMF is also 1 by 3 and the probability of y is also 1 by 3. This is 1. This means with one probability x takes value 1. Okay, so you can see conditioning on, if I change the conditioning even y, even the range changes and the probability distribution changes. Okay, also remember one thing, that if you take x equal to 1, but if you put other values here, like let's say 7, then you know that the numerator will become 0 because there is no probability that x takes 7 and y takes 2 values. For other values, it is just 0. So the whole mass is concentrated only on one point. Okay, so when you look at this function, these two functions, this is a valid PMF. They sum to half, they are both between 0 to 1, right? And you take any Borel set, if it contains 1 and 2, the probability would be 1. If it only contains 1, the probability would be half. Okay, now you see that for independence, it is required that the PMF is equal to the joint PDF is equal to the multiplication of the two. Okay, so from that, if you divide both by PYY, you get equivalent condition that the conditional distribution should be equal to the unconditional distribution of x. So conditional distribution of x given y should be equal to distribution of x, right? So this we get just by taking the original condition that the joint PMF is equal to P of x into P of y, and then we divide both by the PMF of y. So when you divide the joint PMF by Py, you get this conditional PMF, and then when you divide Px into Py by Py, you just get Px. So equivalent condition for independence is that the conditional PMF should be equal to the unconditional PMF of x. Okay, now you see that for this to be equal, not only the values need to be equal, but the range of x it takes should also be equal. Here we see the PMF of conditional distribution given y does depends on the value of y. So this is not a independent, the x and y are not independent to each other. So now let us also define the conditional distribution with respect to continuous random variables. So same way we can say if there are two random variable x and y, both are continuous random variable. If you take any two Borel set B1 and B2, then the probability that x belongs to B1, condition probability that condition y belongs to B2 is equal to probability that x belongs to B1 and y belongs to B2, which is same as saying that probability that the pair x comma y belongs to B1 cross B2. Okay, so this B1 cross B2 is a rectangle. Any point belonging to that means x coordinate is in B1 and y coordinate is in B2. And the denominator would be probability that y belongs to B2. So to compute the probability that xy jointly belongs to B1 cross B2, we have to integrate the joint PDF on this interval B1 cross B2. So if the numerator can be written as the integration on B1 cross B2 of fxy, which is the joint PDF at xy dy dx. Okay, or you can divide them into two different integrals. So first would be dy on B2 and second would be integration on dx over B1. Okay, both are same things. And the denominator would be probability that y belongs to B2. So I can just integrate the PDF of y over B2, or I can integrate the joint PDF over R cross B2. It means that I will integrate the dy on I integrate over dy in belongs to B2 only, but I will add all values where x takes any value in real. Okay, so I will not put any restriction on x. I will add all those regardless of what value x takes. I'm going to add all those density. But in y, I will only consider reason where y takes value in b2. Okay, so if you look this in the graph, this will be a rectangle, b1 cross b2, and this will be a long line, linear. Sorry, it will also be a rectangle, but in one side it will cover the whole real line. Okay, so it's a very long, infinite length rectangle. Okay, now same way I can, if I take b1 as -20 comma x2 and I fix b2, then this will be equivalently as a CDF. So here by definition, if I put this, this will be integration over b1 is -20 comma x. So the integration y is over b2, and the x integration is from -20 comma x. Okay, divided. Okay, and now because this is the integration of dy, I can equivalently write this. I can take this integration with respect to x outside because there is no integration with respect to x here. So this can be equivalently written as integration over dx from -20 comma x of the ratio between this, which is integration of PDF over B2 divided by the integration of PDF of y over B2. Okay, now if you look at this thing, this is a function of x only. You have integrated over y, so this does not depend on, this is not a function of y. Okay, this is a function of b2, yes, but b2 suppose it is fixed. I fixed the conditioning event. So if b2 is fixed, this is no longer a function of y because I have integrated over y, but it is a function of x. Okay, if I change the value of x, this will change. So let's denote this as this function of x. Okay, do not right now focus on what is x, and this means it's just a function gx, let's say, of x. Okay, then we can say that this integration is equal to integration of this function dx from -20 comma x. Okay, and this should be true for any possible values of x because we have not assumed anything specific about x. So you can see that now I can say that for every possible x, this is equal to this. Okay. So where I'm getting with this is that if you can find a function so that you integrate from -20 comma x and you get the CDF, then this function is called the PDF of this density of this CDF. Okay. Or you can also prove this that not just this set. You can follow the same way, and then you can prove that so that the probability of x belongs to b1, condition on y belongs to b2 can be written as the integration of the same PDF over set b. Okay. So if there was no conditioning, then we can, we have said, we've seen this, that we can say that if probability that x takes any value b1 can be written as an integration over set b1, then we say that this is a valid PDF. Okay, this is the density of this probability. But same thing can be said for the conditional also. If given b2, you can show that for every set b1, probability x belongs to b1 given this conditioning is equal to the integration of some function, then this is the density of this probability measure. This is the conditional density. Because this is the conditional probability, this is called the conditional density of x given b2. Okay, and it is formally defined as this way. So just to state this, this function given as the integration of joint PDF over B2 divided by the PDF of y over B2, this ratio is a function of x, and it is a function such that if you take any set B1, then the probability that x belongs to B1 condition on probability that y belongs to B2 is given by the integration of this. Okay, because this is also a probability measure. We have shown that conditional probability is also a probability measure. So this we have denoted as P dash x belongs to B1, which just means that this is a probability x belongs to B1 given y belongs to B2. Okay, so this is called the conditional probability measure, and this is the conditional density of that measure. Okay, so this is also sometimes we also say this is the density of the CDF. Okay, so this is the density of this conditional CDF given B2 or the conditional probability measure a condition on B2. Okay, we denote this in the following way. It is the conditional PDF X given Y, we say, and here we say X belongs to B2. So they are one-to-one corresponding. This means X takes value X and the Y is in B2. So I'm conditioning that Y belongs to B2 and computing the density at of this random variable X at X. Okay, so instead of condition on Y, you can also condition on X also, right? So we can say that conditional property that X belongs to B1, condition that X belongs to B2. Okay, that's also a valid notation. Because in any case, both are equivalently represent to some events. They equivalently represent some events in the sample space. So it doesn't matter whether you write in terms of X or Y, it is they're all valid notations. So here specifically, I mean, this is equal to probability that X belongs to B1 intersection B2 divided by probability that X belongs to B2. Okay, and how can I compute this? Here you don't need the joint distribution as such because there is only one random variable. Although you can find any can write in a joint distribution of x comma x, but let's keep it simple. This is just equal to the integration of PDF over B1 intersection B2, and this is the integration of PDF over B2. Okay, so in that case also, if you want to represent in terms of B1 and B2 separately, you can say that this denominator you keep the same way, but numerator you say that this is nothing but the integration of this over B1. Okay, what is this? This is PDF multiplied by indicator that X belongs to B2. Okay, so if you integrate this, this will be only 1 when X belongs to B2. It will be 0 everyone else. So it is equivalent to this. This will only integrate this PDF over B1 intersection B2. Because all the values where X is not in B2, this will be just 0. So they are equivalent way. Just a two way to write this, that instead of putting all the complete set at the limits, I can say I'm integrating B1 over this function. Okay, what is the benefit of writing this notation? If I write this, then I can equivalently use the same approach and write that this whole ratio I can take inside the integration of dx, and I say that this is the integration of bx. Okay, fxx bx, this function divided by v2 dx. Okay, and remember this is a different x. This is just a local variable. Okay, so just for the sake, you could have said this is ud. Okay, so there will be no conflict. Okay, this is separate integration local variable x, and this is a separate local variable x. Okay, so I can equivalently represent in this term. Then I can say that if for every b1, since I am able to write this probability as an integration term, this is the density of conditional density of b1. Okay, so conditional density of x given x value b2 is nothing but the PDF multiplied by the indicator divided by the value that x takes value in b2. Okay, or you can say if x belongs to b2, yeah, then this will be equal to this, and if x does not belongs to b2, then the denominator will be 0, so there will be no density. So when you condition that x belongs to b2, the density that everywhere else becomes 0. Okay, originally x can have a density over the complete line or some other set, but once I condition that x only takes value b2, the whole density, conditional density changes. Now the conditional density can only occur in the region of b2, and all the other places it becomes 0. And to make sure it's a valid PDF, this density scales so that if you integrate this, this becomes 1. Okay, so you think this in this the following way. Suppose x random variable takes value from minus infinity to plus infinity, and such that the positive real line is also take, uh, or let's take a simple case. Assume x takes value between 0 to 1. Okay, it's a uniform probability measure. So it also takes value more than half and less than half. So density is uniform over whole and just 1. Now what I do is I condition that my B2 is 0 to 0.5. So I condition that x is only between 0 to 0.5. Okay. So in that case, what happens is conditional density of x now, there is no density above zero point 0.5. Okay. Because I have conditioned that x only takes value between 0 to 0.5. So there is no way x can take more than zero point 0.5. So the complete density outside this region, 0 to 0.5 becomes 0. And the inside density becomes 2. So that when you integrate 2 from 0 to 0.5, you still get 1. Okay. Up to now, we have seen that case where we have conditioned on the events which have at least some probability. And we said that it is necessary that when you compute the probability of A given B, it is important that B has a probability which is not 0. So that you can define P A intersection B and also probability of B. We will extend this discussion a little bit to include those events which may have 0 probability event for those random variables which are continuous. So recall that for any set B1, probability that x belongs to B1, condition that y belongs to B2 is given by the integration of a conditional distribution over B1. So this conditional distribution is the conditional PDF of this conditional probability measure, and it is defined as the ratio between the integration of joint PDF over B2 divided by the integration of PDF of Y over B2. So this we have seen earlier also. So in the denominator, if you observe, we are computing the integration with respect to integration of PDF of Y over set B2, which is our conditioning event that we are conditioning that Y should is a member of B1, B2. So Y takes value in B2 and I'm conditioning on that. So let us come back, let us come to the case, what if B2 is a 0 probability event? It means that probability that Y belongs to B2 is 0. One example can be B2 is a singleton element containing only one value, Y0. What will be the statement, conditioning statement then? Then I would say that probability, I am interested in computing probability that X belongs to B1, condition that Y is equal to Y0. So normally I say Y belongs to B2, but B2 has only one element. So this is equivalent of saying that Y takes value Y0. So condition on that Y takes this particular value, what is the probability that X will be in B1? So we know that if B2 is a singleton element, the joint distribution, if you integrate it over a singleton set, that is probability Y belongs to B2, it is 0. What can be an example here? The example of arriving of two persons between 2 to 3 p.m. And then in that case, you will ask that what is the probability that one person arrives between 2:12 and 2:15, given the second person has arrived exactly at 2:30 p.m. So conditioning event here is that the another person arrived at exactly 2:30 p.m. and that is a 0 probability event. And then condition on the second person arrival, I am asking what is the probability that arriving of one person is between 2:12 and 2:50. So formally we can write this. Here our y0 is 0.5 because the second person exactly arrives at 2:30. So the outcome for him is 0.5 half. In that case, B2 will be a singleton element containing 0.5. And then I ask this question, what is the probability that X, which is the outcome of the first person, is between 0.2 and 0.25, given that Y is equal to 0.5? If I formally write this, this will be probability that X belongs to 0.2 and 0.25 and Y is equal to 0.5, condition that P belongs to probability of Y equal to 0.5. Now, event that Y is equal to 0.5 has zero probability because Y is a continuous PDF. I'm assuming Y is a continuous random variable. In that case, similarly, X belongs to this and Y is 0.5 also has a zero probability because it's a subset of the event that Y is equal to 0.5. So both will be 0 by 0 and it will not be defined. But intuitively, if you think of, suppose the case when the arrival of both persons are independent, then you can say that I can, even if you're conditioning that second person arrives at 2:30, it's an independent arrival, so this arrival will not change the arrival of the first person. In that case, probability that the first person's arrival is between 0.2 and 0.25 should be just according to its own arrival. And if I assume a uniform probability measure, this means the event that he arrives in this interval of 0.05 should be 0.05. Even if when they are not independent, somehow there is some joint distribution, you can think of that this distribution should be defined, right? Even if Y arrival is zero probability event, but suppose it is fixed, that may change the distribution of X sometime or may not, but still the distribution of X should be defined and I should be able to compute the probability that X comes between these two ranges. So this makes sense intuitively. How does we make sense mathematically? So in these cases, when you faces such situations where you get 0 by 0 kind of thing, we can take help of the limiting cases. What means here that instead of assuming that Y arrival is exactly 2:30 p.m., let's assume its arrival is around 2:30 with some margin. Right. For example, 2:29 and 2:31 between that. Right. So this interval, I'm assuming a 2-minute interval around it. So I can even take this 2-minute arbitrarily small. So let's take the arrival as 2 epsilon. In that case, I will assume that instead of B2, I will take B2 epsilon, which is 0.5 minus epsilon to 0.5 plus epsilon. And when I say Y belongs to this set, it means the second person has arrived in a small 2 epsilon interval around 2:30. Okay. And this epsilon is very small. That is our limiting argument. So in that case, can we compute this? So here, the probability that X belongs to 0.2 and 0.25 condition on Y belongs to B2 epsilon is equal to probability that X belongs to 0.2 and 0.25 and Y belongs to this small interval divided by probability that Y belongs to this small interval. Can we understand this from a figure? Is that if this is if this one is shows the omega for arrival of 2%, where each point shows a particular outcome. In that case, I'm originally conditioned that Y is equal to 0.5, which was this line. Now I'm conditioned that Y takes value between these 2 points. So this will be a small rectangle. If epsilon is very small, this rectangle will converge to a line. I am conditioning on this event. I am only conditioning that Y takes value. So my B is this interval. B2 epsilon is this interval. And I do not care what is occurring in the other cases because I'm conditioning on Y. And then the numerator is that Y is in this range, along with X is between 0.2 and 0.25. So if you mark this, this will be somewhere here. So this will be, a small set will be A intersection B. So what I'm interested in, the ratio between the probability of this small interval, which denotes that X is between 0.2 and 0.25 and Y is in this strip, divided by the probability of the total strip. In terms of distribution, I can write this probability as an integration over this integration of joint distribution over this small rectangle. And this small rectangle is where X goes from 0.2 to 0.25 and Y goes from 0.5 minus epsilon to 0.5 plus epsilon. And joint distribution of integration of joint distribution over this interval. Similarly, the denominator is a probability of this strip, and this can be represented by the integration of PDF of Y over this interval 1. Now in a small interval, so I want to compute this. Now you can think if I take small interval, epsilon goes to 0. In that case, the joint PDF does not change a lot with respect to Y. Right? Y is a very small interval. So joint PDF takes value around it. So I am assuming that in this joint interval, fxy can be represented by the value of the PDF at x and y equal to 0.5. Okay, and also because y is not changing a lot, in that case, the PDF of y is also constant and will be equal by the PDF at 0.5. So I'm taking the middle point of this strip. Right. So I'm taking this middle point in the line, and I'm assuming the PDF is not changing when you change the direction y. Okay, so this is our assumption, and that is true when epsilon goes to 0. So if I replace this in the original expression here, then I will see that this is the integration with respect to B1. So I'm assuming x belongs to B1. I'm taking for a general B1. So this integration with respect to B1 and fxy x comma 0.5. So I'm replacing general fxy with this value where I'm assuming that this is not changing a lot with respect to y. So I can replace the second argument just by 0.5. So I take this and integrate with on this interval. Similarly, on the denominator, I can just integrate the constant PDF over dy. This is same as saying that the probability that y belongs to this small set is just the density at the center multiplied by 2 epsilon. So we have seen this interpretation that if the interval is very small, the probability that a random variable belongs to that interval is just the density at any point, maybe the middle, multiplied by the length of the interval. Similarly on the top also, because the integration with respect to y, it is not changing with y, I can take it out. So this will be equal to this multiplied by the integration of dy on this interval, which is nothing but the length of it, which is 2 epsilon. So this will be integration over b1 of fxy at x comma 0.5 multiplied by 2 epsilon dx. Now this 2 epsilon into epsilon will cancel out, and what I get is a integration of joint PDF at B1 divided by the density of y at 0.5. Okay, so I missed this. This will be Fy and Fy. Now as epsilon goes to 0, this does not depend on the epsilon. So it should take the same limit. So probability that x belongs to B1 given that y belongs to B2. Here B2 is just internal element 0.5. This should be equal to integration over B1 of this particular set. Now 0.5 is a constant, so I can also take it inside the integration. So now you are getting this feeling that I'm conditioning on B2, but I'm computing the probability that X belongs to B1, and that is written by the integration of some function over B1. So this is the density of this function, right? So that's why we can say that this particular function is the density of this probability measure, conditional, and it's a conditional density. So density of this distribution formally can be written as the joint distribution at x comma 0.5 divided by f of 0.5. And for a general value of y0, I can say the conditional density of x given y is equal to the joint distribution divided by the value of PD of y at 1. Okay, so this should be fy. I missed that. This should be all fy. This is the PDF of y. So what does I mean by that it's a density? It means that you can compute, now once you have density, you can compute the probability of x belonging to any set given y takes the value small y. So let me say again that the probability that x belongs to v1 condition that y belongs to y, if I want to ask that if I fix the value of y, what is the probability that condition on that x takes value in b1? So that is given by this integration of this density over b1. So if I take b1 from minus infinity comma x, this will give you CDF because here I am calculating the probability that x belongs to minus infinity comma x, which is same as probability that x is less than or equal to small x. And that is given by the density integration of density from minus infinity to x. Okay, and here we denoted by the conditional CDF, which is a conditioning CDF of x given y of x when value of y is equal to y. And you can check that it's a valid PDF. So if you integrate this from minus infinity to plus infinity, this should be 1. Right? And the reason being because the joint PDF, if you integrate it over dx, it will give you the PDF of 1. So what we are saying here is that this particular density, which is given by the ratio of 2, is nothing but the probability, the density of the probability measure on x. And this is a new probability measure and not the regular one, because regular one, I just assume probability that x belongs to b1. But this is also a measure on x. It is talking about what is the probability that x takes value b1. But here I'm assuming that the y value of y is given. So it has restricted my sample space. Okay. So if you look at this expression, this is the same one-dimensional density. Although you have two random variables, now you have a one-dimensional density. It looks like a measure defined on a line segment. Okay, and that is true. If you look at the sample space, which was actually a rectangle, once you condition that y takes value 0.5, you have reduced the sample space to just a line. Everything which is outside the line cannot happen because y is already given to 0.5. So I'm only restricted to look at the events in the line. And then I ask that if you look at this line, which is y equal to 0.5 and x from 0 to 1, if you only take this line as the sample space, can you redefine your probability measure and sample space? So my new sample space is just this line. And I want to ask, can I redefine the probability measure on this? Because this line still represents different outcomes, which depends on the arrival of x. Arrival of y is fixed, but the arrival of x can still change. So if you look at this line and talk about the original probability measure, the probability measure which was given by the area or any in two-dimensional integration of the joint distribution, the probability measure of this line is 0 because it's a one-dimensional line in a two-dimensional manner. But even if it's a zero probability event, it still has uncountable number of outcomes. Right? A line can still have uncountable values, and those outcomes represent the arrival of x. So even if the complete is zero, I should be able to still talk about a probability measure on this line, because it has a continuous probability measure on this line because it still has uncountable number of outcomes. That is, those outcomes represent the arrival of x on which we are actually interested in. We want to compute the probability that x belongs to b1, which is a measure on the arrival of x. So what I do is I redefine the probability measure on this line by using this expression. I take the joint distribution on that line, divide by the PDF of y. This helps us in reducing this probability measure this density to integrate to 1, which means that once you integrate this density, the overall probability of the line now becomes 1. Okay, so remember this. Earlier, the probability of line was 0. Now, in this new probability measure, the probability of line is 1 because this I'm restricting my sample space to this line only. So this will become our new sample space. So the probability should be equal to 1. And on this line, relatively, I will ask, what is the probability that x belongs to this particular set? And if this was a uniform measure, then you can easily guess that if the line is of one length, then probability that x belongs to this small section should be just 0.05, which was consistent with our original intuition. You can think from the dependent case also, and you will arrive at the same intuition that what we have to do to look at this conditional distribution is redefine probability measure in a sense that this line becomes this new sample space. The probability of this line should be 1,